regular cigar back here. So here, time and space get mixed up. And you should imagine that this is a very fuzzy region that you can't really think about using any concepts you're used to. Back in this region, you can't really make sense out of time. So there's this picture that'll eventually make sense. And you can apply your familiar notions up here, but you can't apply them back here. And the problem of understanding the Big Bang will eventually be to find the laws by which you can describe this whole picture. Even though you can't really apply your intuition to this part of it here, which is what we usually informally call the beginning. I don't know if that shed any light on the matter.
Yes, some.
Actually,
but totally different laws, as you can think of now.
Totally different laws from the ones that we have in our everyday experience.
Yeah.
And even, you must realize that the laws that, as physicists know them now, are quite different from our everyday experience. But I should imagine that there are a few steps beyond that to be able to set up that picture that I was sketching. There's a version of Wheeler and DeWitt which is a little bit more precise, that was by Hartle and Hawking, which they called the no-boundary universe. It kind of inspired the picture I drew. I don't know exactly if it's closer to the truth, although it certainly may be.
A no-boundary universe? What do you mean?
Well, a little bit like I drew. I'd like to contrast this with the notion where time makes perfect sense, but it began. So this is time zero here, and that's the beginning. But I'm going to put a question mark because I'd be pretty skeptical of this picture being right. I'm just trying to draw an illustration.
If you don't define time. Yeah.
Right. But then we imagine at time zero the universe was born and it evolved from there. And then in this picture, there's a boundary of space-time, which is this curve here, and you need to give what physicists call initial conditions. You need to say what there was at the beginning. And then the question would arise, why just those initial conditions were what we started with? Well, Wheeler and DeWitt said this would be wrong because our concepts would be fuzzy near what we usually think of as the beginning. And Hartle and Hawking tried to make it a little bit more precise by saying that there wasn't a boundary, but instead there was a closed world, but which I've roughly drawn here, but what I've drawn is a hybrid of several pictures, including theirs. And then we want to say that, once again, as Wheeler and DeWitt did, that near what we think of informally as the beginning, our concepts that we're accustomed to in everyday life are so far off that you can't speak about space and time in any sense that we're used to. And in particular, the usual paradoxes, like what was there before the clock started, don't make any sense. By the time the clocks and the time make any sense, you're way past this stage. And you're observing the Big Bang from afterwards.
Yeah, it's kind of a strange idea that you leave space and time out. For us, space and time, for me as a layman, it's kind of, okay, it's part of physics.
Right.
Now, you're lost.
Well, a lot of things that we take for granted prove to only be approximations in the 20th century.
Yeah. We're now talking about quantum mechanics and the beginning of time, or the beginning of something we call the world of the universe itself. We can't say the beginning. Even the phrase the beginning is possibly
well, you can
wrong.
certainly, yes, that's right. It's imprecise, but you can talk about the beginning of the phase that we see the universe in now.
Yeah.
But that doesn't involve the usual naive paradoxes like who started the clocks. You go far enough back, and the laws as we know them now don't apply. The universe is hot and dense. And then it's when you want to ask how it really started that you probably run into this notion of the fuzziness of our familiar concepts of space and time.
If we are looking for a little while before we go over to strings and the beauty of it, to the end of the universe, or the present state of the universe.
Yes.
Could it be, as Steven Weinberg asks himself in the Dreams of a Final Theory, that the present expansion of the universe will appear as merely a fluctuation in an eternal but constantly fluctuating universe that on average is always the same?
There are versions of the inflationary universe, for instance, which make a notion like that precise. So it's conceivable.
But what's your opinion? What kind of universe are we living in?
Well, the scientific article that made the most impressions on my thinking about the far future was by Freeman Dyson 20 years ago, where he tried to imagine the far future of the universe. So you see, in the context of general relativity, you've got the expanding universe, which of course we discovered experimentally around 1920. But we don't yet understand the cosmology well enough to know if the expansion will go on forever, or if eventually the universe will recollapse. It used to be...
Or even that those assumptions are wrong? Expanding or...
Well, possibly they can be criticized, but let's, for the moment, accept that dichotomy. People traditionally believed that either way life would go on only for a finite length of time in the future, because if the universe recollapses, it gets hotter and hotter, and we get boiled to death and eventually crushed. And in the other case, where the universe expands forever, it keeps cooling down, the stars burn out, we run out of fuel. It's even worse than running out of oil, we even run out of stars. And we freeze to death. Now, as far as I know, the first part is true, that if the universe recollapses, we get burned and eventually crushed. But Freeman Dyson argued in a fascinating article 20 years ago that in the ever-expanding universe, although it's cooling and the stars are burning out and so on, so that life in the present form couldn't survive forever, he argued that life could evolve and adapt so as to go on forever in ever-changing forms. Now, it's a little bit bizarre compared to what you're used to. You've got to get bigger and bigger. You sleep more and more. You move more and more slowly. But nevertheless, if not as an individual, then as a species, you get to think more and more thoughts and live more and more deeds, experience more and more things, and possibly communicate with more and more distant civilizations, maybe even travel there. So I found it a fascinating story. And once I was told that the alternative wasn't death by ice or death by fire, as it was sometimes presented, but that the alternative was death by fire or an ever-changing existence, evolving into forms we can't easily conceive of. I find the second one so much more preferable. But ever since then, I've actually found it hard to believe that the universe is going to recollapse. And there's a very interesting subtlety, which Freeman actually didn't address, but I've discussed it with him a few times, that has to do with something called the cosmological constant, which is the energy density of the vacuum. It's one of the puzzles that came up in Einstein's theory, which neither he nor his successors have been able to grapple with successfully. And it's one of the questions that actually fascinates me most about physics, which is why the energy of the vacuum is exactly zero. So, it has to do with the fact that if that wasn't so, then general relativity would be very obvious in everyday life. Space and time look like they're almost flat, such that it took Einstein's brilliance to realize that, in general, matter curves space and time. But if the cosmological constant were not zero, the curvature of space and time would be obvious in everyday life. And the three angles in a triangle wouldn't add up to 180 degrees, like you were probably taught in high school, but they would add up to something that would depend on the area of the triangle. So, it's really, for a variety of reasons, a quite important scientific question, which is completely unsettled. Why the cosmological constant is zero. But it has the fascinating consequence that if it isn't zero, life can't go on in the far future, because you get blasted to bits. So, there are other reasons, actually, that I suspect that the cosmological constant is really exactly zero in nature. It's not universally shared. There are lots of astronomers who suspect that's extremely small, but not exactly zero. And if that's the case, then our distant descendants, through no fault of their own, will be blasted to bits. Or maybe even frozen first. But I find it comforting that the case that I suspect anyway, that the cosmological constant, or the energy of the vacuum, is exactly zero, is the case that Dyson's scenario really needs to make this ever-changing and ever-evolving life possible in the future.
It's a wonderful idea.
I think the credit goes to him, not to me, but yes, I agree it's a nice idea.
But it doesn't apply to us.
Well,
we are lost.
Yes, well, yeah. I've got to with that. That's where we perhaps have to look for some consolation in beauty. but I think that this is the one instance, actually, where a philosophical judgment has some influence on my evaluations of science. Because the notion of our descendants being blasted to bits or burned when there's a perfectly good option where the universe expands forever and the cosmological constant is zero is so grim that I find it hard to believe either of those are true. And in the case of the cosmological constant, it really interacts with my scientific work a lot. In other words, having a hunch about what the answer is going to be often gives you some clues about how to try to solve a problem. And in this case, suspecting that the answer is zero guides a little bit my choice of attempts to solve the problem.
Yeah.
Where someone who suspected it was extremely zero but not zero would look at somewhat different avenues. At the moment, neither of us has been proved right, because no one has succeeded in explaining either that it's exactly zero or that it's fantastically small but not exactly zero. But I, of course, follow the route that I think is more promising. And I've indicated, in terms of contemplating the future, one of the reasons I think it's more promising. There are others that are more technical.
Een donderdagmiddag in het Magische Instituut for Advanced Study in Princeton, Verenigde Staten. De thee wordt geserveerd tussen 3 en half 4 in het hoofdgebouw. De stilte, zowel in het gebouw als rondom, is oorverdovend. Denken maakt geen lawaai. Wat Witten tot nu toe vertelde is prima te vatten. Maar dat gaat even veranderen als hij na de thee de superstring-theorie zal uitleggen. Slechts een paar dozijn van de 5 miljard mensen op aarde is in staat te begrijpen wat hij bedoelt. Zoals Freeman Dyson zei toen hij jaren geleden een openbare lezing van Witten hoorde over superstrings. Ik ging verbijsterd weg. Ik wist dat er iets ongehoord belangrijks verteld was, maar ik kon het niet omvatten. Dit is een intelligentie die ver voor de onze uitloopt. Witten zal zo direct uitleggen wat zijn superstring-theorie inhoudt. Vriend en vijand zijn het erover eens. Als er een doorbraak komt, in de jacht naar de finale formule, dan is het die theorie. Neem de natuurkundige en Nobelprijswinnaar Steven Weinberg.
I think the most likely possibility
Strings?
is strings, yes. I think the most likely possibility is something like a string theory. But these days, the string theorists have gone beyond string theory. And I think you'll be talking to Edward Witten later, and he is one of the leaders in this recent development. Some years ago, I would have described string theory as saying that the fundamental entities of nature are little one-dimensional rips in space-time. Think of them as little strings, but without any string, just the line which vibrate and go traveling around at the speed of light, and their different modes of vibration are what we see as different types of particle. Mm-hmm. A string vibrating one way will be an electron, and if it's vibrating another way, it will be a photon. These days, string theory itself is seen as a low-energy approximation to a more fundamental theory, which I guess we still call them string theorists, are having difficulty in formulating. I would say that they're at the furthest, they've gone to the furthest extent possible in pushing purely mathematical intuition beyond any realm where experiment has anything to say, to try to formulate a theory at the most fundamental possible level. And I regard it as the most hopeful direction and most exciting thing on the fundamental level in physics that has happened in a long time. But I'm not one of the important figures in string theory, to say the least. I've written a few articles about string theory of monumental unimportance, and written mostly for my own educational purpose, to do some calculations so that I know what the theory is all about.
Neem de natuurkundige en Nobelprijswinnaar Leon Lederman.
My judge of superstrings is obtained by watching the facial expressions on Ed Witten's face when he talks about it.
He once was here.
Yeah, not long ago.
From. Yeah.
He's a leader. I'll follow him anywhere.
strings are a candidate for a final theory or not?
I'm not competent to judge it. As I said, whenever I listen to a string talk, I always think of, I try to feel better by thinking about wire chambers or something you can build and measure.
Because strings are,
Well,
you will never see them.
Oh,
Even
you'll never
if-
see them, but that's not so puzzling. We don't see even the particles they replace. You're talking about a point or something smaller than some incredibly small number, 1 followed by 35 zeros.
Yeah.
And he says, well, that's not really a point because stretch it out to a little string. You're not going to see that either. But there are many other concepts in this which are more visionary than the fact that these are not points but strings, that they have to do with the number of, the dimensions. This business of compactification, where there are not the 3 space dimensions and 1 time dimension that we know and love, but there are 10 dimensions, and some of these are curled up in some way.
Yeah.
You
Make
take
them
this
disappear.
unimaginably small string and you curl it up to make it disappear. There are muscles in your mind that have never been used before, and they hurt when you try to use them to understand these things. And again, they're words to describe in mathematics. But we're waiting for some kind of prediction that they'll make, and they haven't really been able to produce predictions yet. Although, as Witten points out, there's a kind of consistency. The superstrings is not inconsistent with the world being the way it is.
Neem de natuurkundige Freeman Dyson.
Witten has invented this marvelous tool, which is mathematically extraordinarily rich and
Coherent, beautiful.
beautiful. It has led to a lot of first-rate mathematics. But it could very well be that it turns out in 100 years that it is made use of by nature, but in a totally different context from the one that he's thinking about. And I wouldn't find that surprising.
Is het te begrijpen wat Edward Witten bedoelt met zijn superstringtheorie? 3 natuurkundigen. Ze aarzelen. De wereld die Ed Witten creëert, alleen door te denken, is zelfs voor hen nieuw, vreemd en deels ongrijpbaar. De taal waarin Witten de oorsprong van ons universum probeert te beschrijven, is een taal die zelfs voor zijn collega-kopstukken vreemd is. Misschien verwoordt de hersenwetenschapper Gary Lynch het best wat u de komende minuten zult gaan zien.
Richard Feynman, the physicist at Caltech, had the greatest introduction to a textbook I've ever seen, which went like this. First sentence, practically. Notes on physics. And he says, okay, this is about quantum mechanics. Don't think you're going to understand this. Nobody understands this stuff. I don't understand this stuff, and you're certainly not going to understand this stuff. And by that he meant you're not going to, in a Kantian sense its correctness. It's too bad that Kant didn't get a chance to see that, because I think that would have caused him some serious problems, and it causes scientists serious problems. It's funny though, in the quantum world, these guys reached a point through effort where they at least can feel the truth of it, but the rest of us can't share it, and that's what I think is the break. As I said to you yesterday, I would bet you a month's salary that the first insight we get, the first brain-based cognition theory, because I don't think we have any, but the first one that grows naturally out of brain science will be something that we won't understand. We won't have that shared sense of beauty and of truth. We'll just go, that's the way it is, and I can't put it in language that we can share. I will bet you that's the way that turns out. In fact, I think it's already starting to shape that way. So maybe in the brain sciences, ultimately at the end of the day, at the turn of the millennium, maybe we'll arrive at our own kind of quantum strangeness. And that's okay. I feel bad for Kant, perhaps, if he was to watch this, and I've probably got him mixed up anyway, but I think that's okay. I think that's okay. if in the end of the day we realize that the 1500 cc brain cannot understand itself in conventional language.
De komende 20 minuten vallen moeilijk te omschrijven. Witten begrijpt ze zelf nog niet helemaal, althans, hij heeft nog grote moeite met de implicaties. Ze gaan over de oorsprong van alles. Meer kun je er voorlopig niet over beweren. En vervolgens naar de superstrings, de ultieme formule voor het universum en God, rest alleen nog die ene afschuwelijke vraag, die Witten niet kan of wil beantwoorden.
Shall we go to the majestic and still mysterious theory?
Sure.
Before you explain what superstrings is about
Yes.
and its beauty, tell me what is the beauty of one single string?
Well, the idea in string theory is that elementary particles, instead of being point particles that obey quantum mechanical laws, are little loops of vibrating string that also obey quantum mechanical laws. And the beauty of that is that it describes many different things all at once. If you've got, for instance, a violin string or a piano string, they have many different modes or harmonics of vibration. If you pluck a string which is at middle C, for instance, you also see the higher harmonics. And that's responsible for the beauty of music. The reason we have symphony orchestras and not just tuning forks is that different instruments excite the higher harmonics in different amounts. The pure tone of the tuning fork sounds garish and ugly to the ear. The rich sound of a violin comes from the mixture of the different harmonics. Now, in the case of the string, you've got this one vibrating string. It has many different harmonics, and we perceive those different harmonics as different elementary particles. So, for instance, the electron, the quark, the photon, the neutrino, the graviton, all these things are different modes of vibration of a single string. And that's very beautiful and harmonious, getting the different particles from different forms of vibration of a string, just as a musician gets the richness of the tone from the harmonics of the violin string.
How small is a string? If I say small means in this case that the superstring is looks up at an atom,
Mm-hmm.
as an atom looks up to the entire solar system. Am I right?
Something like that. We don't understand exactly how small they are because we don't understand the theory perfectly. But roughly speaking, the proportion of the solar system to an atom is like the proportion of an atom to a string.
That's small.
That's pretty small.